Okay. But before introducing random variables, let's review what we have studied so far. So first we studied logic, propositional logic. Then based on that, we studied set theory. Then based on that, we defined sigma algebra and sigma algebra. And based on that, we define probability measure. Okay. Okay, but why do we need all this? Because we needed logic to define the language of set. We describe definitions of sets using the language of logic. Then, of course, sigma algebra is a kind of algebra of sets. So, of course, we need set theory for this. But why did we need sigma algebra for probability measure? That is because probability is always a probability of events, right? Probability is always a probability of some events. And we define these events as subsets of some universal set called omega. So that is sample space, right? Sample space. So we define a sample space as a set. So it can be any set. And events are subsets of sample space. So, but probability cannot be defined for any kind of subsets. Those subsets for which probability can be defined must satisfy some properties. And those properties are summarized as the axioms of sigma algebra. Okay, only those subsets that satisfies the axiom of sigma algebra can be used as events for calculating probability. Okay, and based on these concepts, we now introduce random variables. So random variables. So what are random variables? Actually, in high school level, we didn't define random variables very formally. It's a kind of variable that varies randomly. That sounds like a good definition of random variables. But what do you mean really by randomly uh, variable? I mean, something that takes randomly different values. What do you mean by random? Actually, defining randomness is very difficult. And in our formulation, we totally avoided the definition of randomness. You know, of course, this sample set is a set of all possible outcomes which can happen randomly, but we didn't directly define randomness. So, while avoiding randomness, how can we define something that varies randomly? Actually, although random variables are called variables, they are not really variables. They are actually functions. So before defining that, we introduce some concept called inverse image. Let's say if we have two sets, x and y, and we have a mapping between x and y from x to y, then take a subset of y. So this is, say, B. So B is a subset of y. Then we look for all the values of x which map into this subset. Okay. So for each element of this subset, there must be a corresponding value here. I mean, it can be empty set if this f is not surjective. But anyway, we can find some value, possibly no values. So this subset of x is called the inverse image of B by F. And this is inverse image of B by F. And we write as this. So this is a subset of X such that each element of this subset belongs to this subset of Y, B. Okay. So if you pick any element here inside this, it will be mapped into inside B. So that's what this inverse image is. Okay. Now, don't confuse this inverse image with inverse mapping. They're different. Inverse image can be defined for any mapping, but inverse mapping can be defined only for bijections. Okay. So inverse mapping is a mapping. We also write like this, F inverse, but this is not subset, but it's a element. It's an element of Y. So this is element of X, and Y is an element of Y. So this is Y is an element of Y. This is mapped into some element of X. Okay, so if this F is a bijection, we can map each element of Y into exactly one element of X. But this cannot be defined unless this F is a bijection to begin with. Okay, so these two concepts are different. Okay. Then, using this inverse image, we define measurable functions. Okay, let's say this omega and F is a measurable space. Remember the definition of a measurable space? So this omega is a sample space, and this F is a collection of subsets of omega which satisfy the axioms of sigma algebra. Okay, so this F is a sigma algebra. Then let's say we have a function from omega to real numbers. Okay, so we have omega on one hand, we have real numbers on the other hand. So we have a function from omega to real numbers. Then this F is called a measurable function if its inverse image of this interval, alpha is some real number, belongs to belongs to the sigma algebra. Okay, so this is an interval of real numbers. Okay, so that means if we pick, okay, let's write the definition of this subset. This is a subset of omega such that the value of this function is greater than alpha. So this means this value is in this interval, right? Same thing. So this means same, this thing. Okay, so we pick a subset here, then take that subset into the original sample space. So this defines a subset in omega. If this subset belongs to this sigma algebra for any subset here, okay, whatever the value of this alpha is, always we can find a subset of omega which is an element of the sigma algebra. Then this function is called a measurable function. So why is it called measurable? Because elements of sigma algebra, so which are subsets of omega, are called measurable sets, right? Measurable means it can be measured by some kind of probability measure. Okay. If it's not measurable, the probability cannot be defined. It's not defined, so it's not measurable. I mean, it's tautology, but that's what it implies. So if we pick any subset of real numbers, then get the inverse image of the function. And if this inverse image is a measurable set, then this function is called a measurable function. Okay. And now we can define random variable. Random variable. A random variable is actually nothing but a measurable function. So random variable is another name for a measurable function. So, we don't define randomness, but we can assume that we can pick any random elements here. Then we calculate the value of this function for any outcome in the sample space. Then this will give you some value, real number. So that looks like it's varying randomly. So this is random variable. Okay. Now we want to make one distinction between different random variables, different kinds of random variables. One is discrete. The other is continuous. Okay, so if we have a sample space and real numbers, and we have a random variable, which is just a measurable function, and if the values of this function are discrete, I mean, that means all the possible values of this function is at most countable. Then it's called discrete. Otherwise, it's called continuous. So that means, for example, if this sample space is countable, then the value of the possible values of this random variable is also countable, right? Because the number of possible values cannot greater than the number of elements in the sample space. So in that case, this random variable should be discrete. But if it can take all, for example, all real numbers, possibly take real any real numbers, then this random variable is continuous. Okay. Well, it doesn't have to be all possible real numbers, but yeah, I mean uncountable number of real numbers. Then this is continuous. Okay. Let's see one example. That is this table. So this table shows the frequency distribution of litter size in rats. Here, litter means the number of babies one rat gives birth to. Okay. So this table shows 7 rats gave birth to one baby at once. And for example, 121 rats gave birth to 7 babies at once, and so on. Okay, so this 1, 2, up to 12, this is the number of babies born at once, at the same time. Okay, and these numbers are the rats, mother rats, that gave birth to this number of babies. Okay. So in this table, there were total of 815 rats that gave birth to some number of babies. Okay, and if we divide these numbers, number of rats here, by 815, we get these relative frequencies. So intuitively, these relative frequencies may be considered as the probability that a rat gives this many number of